A lot about nanoparticles as an introduction. Then I will say something about how to prepare these kind of small particles or dispersions on emulsions. Have looked at for some food applications and existing products on the market to come to some conclusions and future perspectives. Talking about nanotechnology, well, actually there is not a kind of a one single very strict definition, so that makes it a little bit complicated, and actually the definition already also will depend a little bit on the field, for instance. Considering, for instance, microelectronics, then, for instance, well, then typically there is in the definition there is the reference to the kind of size range from 1 to 100 nanometer here. So as you can read here, it says nanotechnology is about the manipulation of matter with at least one dimension in that region here. And actually that 1 to 100 nanometers is also, well, it's largely due to the fact that if particles become very small, that they begin to have some kind of special properties. That's, for instance, here illustrated. A typical example is, for instance, if you consider the color of a gold salt. So actually what you have in this is water, but with small insoluble particles of gold. And actually, depending on the size of that gold particles, actually you see microscopically a different color. So here from the color already you can have an indication of the size. So with bigger particles having a kind of a blue appearance and smaller particles having a red appearance. So here you see already that size indeed can have an effect on properties. Actually, if you go to the lower end, one of the well-known examples of nanotechnology was actually that here the logo of IBM was created, and that's actually just by putting xenon atoms on the surface, and actually so by having a combination of individual atoms. So then we're going to really small scales. Actually, that logo was created actually under a microscope. I said already that there is not kind of a single definition, so that's a kind of an overview here with definitions from different agencies, United States. There again you see that it says dimensions of roughly 1 to 100 nanometer. Here again saying from actually that unique phenomena that you have. The U definition that was used here in the 7th framework program, but actually there it doesn't refer anymore to a specific size, but it rather says that it's actually, there you have, actually again refers to the fact that you have that kind of size-dependent phenomena, so that you come in the region where size plays a role here. For the rest it's quite long, so it's actually a kind of a summary of all things that can be included, where for instance also techniques for characterization also are part of nanotechnology, actually quite diverse. Alright, anyway, I'm not going to read all of this, so it's actually included for your information in the presentation. Anyway, what you'll see from what is common in all of these definitions is that actually, well, it's already saying that nanotechnology is actually about doing something and actually specifically making something, so handling, controlling manipulation of matter at a small scale. So that actually already says that if you have small particles which are present naturally, that's not really considered as nanotechnology then, according to these definitions. About size, you will see in different definitions that at 1 to 100 nanometers returning, but quite frequently also saying from, it's actually not a strict guide, it's actually more about indeed having a kind of special, having so small particles that they have some special properties, and that is roughly corresponding to being smaller than 100 nanometers, but actually there is other factors that play a role, like for instance also density, so it's, in that respect, it's not a strict limit on particle size. And actually, it's especially about having new applications then, which is important in this kind of definitions. Here we see something different. Well, that's actually here again from the European Commission. That's actually then talking about when is something considered as a nanomaterial here. And there again, well, we see that it's well, complicated to define something. Here it says that the nanomaterial here is a natural incidental manufactured material containing particles. Okay, that's okay. In an unbound state, or as an aggregate, or as an agglomerate, so that's already makes it complicated. And it says then where for 50% or more of the particles in the number size distribution, one or more of the external dimensions in the size range of 1 to 100 nanometer. And anyway, there we have again that one. But you see already here that trying to define something is actually quite complicated. And then actually they're trying to quantify it, because here it says at least 50% by number should be smaller than 100 nanometer. The thing is that to measure this on a commercial product, which is a mixture of everything, that even becomes more tricky. Okay, we had that kind of quite up to now, most of the definitions were somewhat referring to the 1 to 100 nanometer range. But then especially if we go to food technology, and actually the same holds for pharmacy, then actually mostly definition is quite extended. And then typically, for instance, if you read something about nano suspensions, nano emulsions, nano dispersions, well actually in this kind of fields, nano is like considered as being smaller than micro. So if it is smaller than a micrometer, then quite frequently actually it's considered already as kind of nanoparticles here. And that's especially holding for in pharmaceutical field. You will see a lot of publications about so-called nanoparticles, which then just refer to the fact that they are smaller than a micrometer, or even that the majority of the particles is smaller than a micrometer, so that there can be even a fraction that is bigger. Now, what is returning in that case is that, we said at the beginning in the definition, nanoparticles are particles which are so small that they have some kind of special effect, some special property. And actually the special effects that you mostly have in that case, if you go smaller than a micrometer, is that actually the effect of gravity becomes much less important. So that's actually so that you don't have a problem of sedimentation or creaming, which is actually explained in some more detail in the next slides. Of course, what you know is if you have big particles, for instance, and there indeed the 1 micrometer is typically considered as a limit, as I will also show in the next slide. If you have big particles, then typically particles will have a tendency to gradually sink to the bottom if they have a higher density than the liquid. Or the other case can happen if your particles have a lower density than the liquid, then they have a tendency to go up. That's, for instance, that creaming phenomenon is typically happening with milk coming directly from the cow. Your fat droplets are several micrometer in diameter, and over time they're gradually going up. And so that's actually what is quite normal. Now the effect is, on the other hand, that there is not only the gravity effect, and there the velocity is proportional with particle size squared, so that's actually why particle size is important. But there is actually also a counteracting effect, which is Brownian motion. And Brownian motion has the effect of trying to have a kind of a uniform distribution of your particles over the whole volume. And actually for Brownian motion, also the speed is quantified by the diffusion coefficient, which is actually inversely proportional to particle size. So it means that effect becomes more important as particles become smaller, so they have just a kind of an opposing effect. And it's indeed due to that one, so due to this second effect, that makes that indeed if you have particles smaller than a micrometer, roughly spoken, that actually they can remain homogeneous. And of course there the typical example is again the milk that you normally find in the shop, which does not show any kind of creaming anymore. That's because that milk was homogenized, and actually in that homogenization process, typically your droplet size is about reduced by a factor of 10. So originally in milk you have droplets of several micrometers, which are susceptible to creaming. If you reduce the size to only a couple of hundreds of nanometer, 0.1 to 0.5 micrometer, then actually the Brownian motion becomes the most important factor, and then actually you do not see that creaming anymore. So what you see really here is that actually, homogenized milk could be considered as a kind of a very old example of nanotechnology, because actually also by changing the properties, the size properties, you change actually the properties of the overall product. So it fits actually to some extent the definition of nanotechnology. All right. This actually is a kind of a more detailed explanation of what I said in words in the previous slide. What is calculated here is, you see along the y-axis, it considers the displacement of particles over a period of 1 second here. Calculations here were done for particles with a given density, 2000 kilogram per cubic meter, in basically water at room temperature, density of 1000 kilogram per cubic meter, and the viscosity is the viscosity of water at 20 degrees. And so what it shows then is what is the distance that particles move over 1 second due to the gravity effect. And we have seen that actually the velocity there is increasing in particle size. Well, the velocity is proportional to the diameter squared. So that's what you see here. Your distance traveled actually increases quadratically with size. On the other hand, we have seen that Brownian motion plays a role, and Brownian motion means that your particles move at random, and that was inversely proportional with size. So that's actually your distance traveled by Brownian motion here. And then indeed, you see that you come to that kind of range of about 1 micrometer. That actually says for smaller particles, actually the Brownian motion is more important than gravity. So that means that your dispersion remains homogeneous, that your particles move especially in random directions and not just going in one single direction to the bottom or to the top. Whereas actually if you have bigger particles, then that critical region of about 1 micrometer, then actually your particles then mainly will be subjected to the gravity effect, because their Brownian motion becomes less important. So you see actually here that indeed size is very important. Of course this graph will depend, because especially for the gravity effect, that also strongly depends on the density of the particles, so that 1 micrometer also here is not a strict boundary, but it depends on the other properties of your particles. Okay, so actually, in the more general case, we're talking about small particles with some kind of special effects due to being so small. The special effect here quite frequently being that actually gravity, so sedimentation or creaming, becomes less or not relevant anymore here. And so the question could be, is it new? Well, I said already, I already used the example of milk and homogenization of milk, which shows that it's not new. Actually, also, well, if we use that kind of definition, that's basically also coming back to the definition of colloidal dispersions of colloids, because colloids are also like defined as particles where the effect of Brownian motion becomes more relevant than gravity. Talking about, for instance, about nanoparticles, so particles in that region, well then, for instance, if you have a look for skim milk, actually, skim milk means that fat droplets have removed. Actually, skim milk, visually, it still looks very opaque, completely white, and no light is going through. That's because actually there are still particles present, and the particles that are still present in skim milk are actually the casein micelles, so aggregates of your casein proteins, which are typically have a diameter of about 50 to 250 nanometer. So there are actually also some kind of nanoparticles being present in milk in a very traditional product. And for instance, even if you would have a look, go somewhat further, actually in milk there is about 80% of your protein is in the form of casein, which is included in that casein micelles. But about 20% of the protein is present as whey proteins. And actually whey proteins are only a couple of nanometers in size. The whey proteins, that's actually the one that is, if you're making cheese, then actually the liquid that remains is called the whey. So that's basically the water that contains the lactose, the sugar, but also the protein is present there. But in that case, your protein particles are so small, a couple of nanometers, that you don't have that opaque appearance anymore. But also they fit basically within the definition, or within that range of 1 nanometer to 1 micrometer in that case. So it means nanoparticles, it's surely not that they're completely new and that they had not existed before. There are a lot of examples being present. Of course, new nanoparticles are created, so it doesn't mean that there is no health issue at all, but just actually to show you that nanoparticles are also present just in the products as we know them already a very long time. That's actually a kind of another overview again, showing you here that typically, if we're talking about nanotechnology, we're in that region from 1 nanometer to 100 nanometers, or sometimes going up to 1 micrometer. And for instance, here what it also shows you is some other kind of examples, with, for instance, hemoglobin, here having a size of a couple of nanometers. DNA, the diameter of the DNA strands being, for instance, something like the order of 10 nanometers. Virus particles being typically 100 nanometer. So again, showing you that there's quite some examples in nature of structures which are in that kind of nanotechnology range. Okay, so that's about nano particles. If we then come back, so in the title there was referred to nano dispersions and nano emulsions. If they are dispersed in a liquid, then we talk about the nano dispersion. So basically also your skimmed milk is a nano dispersion. You have that casein, micelles, which are dispersed in the liquid matrix. Nano dispersions, that's in general, so if you have particles present in a liquid, and then depending on the properties of the particles, if the particles are solid, then we also talk about nano suspensions. Whereas actually if the particles are liquid, if they have, for instance, small oil droplets in water, then we talk about nano emulsions. So that's depending on the physical state of your particles, the dispersion is a suspension or an emulsion. The third case here is a kind of a special case, which we will come back to in the preparation. This is that your particles could also be different than in just liquids or solids. They could also be just surfactant aggregates, which are that highly hydrated here, such as, for instance, micelles. I've indicated here kind of a product which is called micellar water, which is, for instance, used in cosmetics to remove makeup because of the micelles, which have very good solubilization properties, so they can nicely entrap hydrophobic materials here. Here you see another example, so vesicles, also called liposomes, or sometimes lyosomes. Here you see, for instance, a product that contains liposomes, which are actually also surfactant aggregates, but I will try to explain that somewhat later on. So there are quite some different types of nanoparticles present. That's what I want to show you. Okay, that was kind of a general introduction. What about nanoparticles? What types are present? So let's switch to the second part, which is actually about how to prepare this kind of small particles here. And actually talking about preparation, it's actually important that there's like two quite different approaches. Actually, on the one hand, you can start from bigger particles, which are gradually then removed in size. So that's kind of a top-down approach, which is said, which actually remove quite some energy input. Basically, the high-pressure homogenization of milk is a kind of an example of that one. You start with fat droplets of several micrometer in size, and by putting in a lot of energy, and actually the more energy you put in, the more you can reduce the size, so you can go from the top down in that case. Whereas, for instance, in other cases, that would be especially for that kind of surfactant aggregates, micelles and liposomes. Basically, there you start from individual molecules, which then are gradually aggregated, gradually coming together and forming bigger structures. So that's a kind of a bottom-up approach. And the big advantage of that one is that actually there is much less, or quite frequently, no energy input needed. For instance, if you dissolve a surfactant in water, then quite frequently it will spontaneously form micelles. If you do your dishwashing in the evening, you use a little bit of detergent, you add it in the water, and actually automatically it will form the micelles. And again, actually the micelles there are again used to take up the fats from your plates. For instance, so your micelles are actually good for encapsulation of hydrophobic material and enable you to remove the fat and the grease from the materials. Okay, so two approaches. For instance, well, quite frequently to make emulsion, so liquid droplets with a sufficiently small scale. Then typically, so you're starting from a coarse emulsion from big droplets, which are gradually reduced in size. And then typical techniques that are used are, for instance, ultra-turx, which is actually a kind of a rotor stator mixer. So what you have in that case is that you have a stationary part, so the outer part is actually not moving, so that's your stator. The inner part is moving at a high velocity, and basically your emulsion is sheared, so in the small gap between the two, it's sheared actually at a high intensity, and so there you have your droplet breakup. Ultra-Durax, that's typically, so that high-speed mixing, that's typically a kind of a first step, so to already partly reduce the size, but then actually to really come to very small particles, then you need to have more powerful techniques, where I mentioned already the high-pressure homogenizer, which is used, for instance, so in milk, but actually in milk you do high-pressure homogenization at still quite low pressures. If you go to higher and higher pressures, you can actually more and more reduce the size and come to very small emulsion droplets. So then you squeeze actually your coarse emulsion at very high pressures to very small openings, and it's actually as your emulsion is squeezed through that small openings that actually there is again a high shear and high velocity gradients created, which break down your emulsion droplets so that you come with much smaller droplets. Microfluidization is actually another technique which is now already also available several decades. What you do in that case is that you have a kind of a micro channel, so the emulsion is pushed at high velocity through small channels. Your channel is actually split up in different parts and then again combined. And so actually here in this combination part, so where your two streams are actually impinging with each other, it's basically here that you will have your particle size disruption effect. But basically you're in the degree of size reduction, basically these two techniques are quite compatible. But microfluidization is typically still used on a smaller scale, so for instance for pharmaceutical applications you will quite more frequently see that microfluidizer as a technique, whereas actually for larger scale applications then more typically the high pressure homogenization technique will be used. Anyway, what you're doing there is, so as I said already, you need mechanical energy to go from big objects to smaller objects. Here, so there you gradually reduce size. Here, now of course there is a kind of a problem, which is that because now maybe it looks like simple, okay, you reduce size, but actually if you just disperse oil and water, then actually the moment that you stop putting in your energy, then actually it could well be that gradually over time again droplets will fuse and finally can again lead to a complete phase separation, which normally will be a kind of a spontaneous process. Normally, actually, if you have a look for the free energy of a system, that's actually the preferential state, that's the state of lowest energy, and actually an emulsion state is always a state of higher energy. That was actually the reason that you need so much of energy input to create your emulsion. The driving force for that one is that actually, well, the interfacial area, so the area between, for instance, your oil and water in an emulsion is actually much bigger, typically actually of the order of some hundreds or even some thousands of square meters per liter of emulsion here, which means that you have about the size of a football ground here. Whereas actually, if you have a demixed state, then the interfacial area between your two liquids, that's actually very small. And actually interface, that's actually not favorable, so that's indicated here. The problem is that the interface is unfavorable. Actually, molecules sitting at an interface are in a higher state. That's, for instance, also the reason that, for instance, what I show in this picture is droplets of mercury, which adopt a very spherical shape. That's also because actually here your objects try to minimize the interfacial area, and that's actually by taking the spherical shape. I've used another kind of example. It looks a little bit like if you have a herd of sheep. Actually, also there in that case, typically if it would be a dog around, then actually also there being at the interface is not very favorable, and actually also actually the sheep will try to hide at the inside. Well, it's a little bit comparable with molecules that you have there. Basically, your oil molecules, they do not want to have contact with water, and actually they're trying to prevent the contact, which is actually the reason for the fact that normally small droplets will have a tendency to grow, to stick, and to fuse. So normally that small particles with cold area are not favorable, so typically there you will actually need a kind of additional stabilizer, you will need something to prevent that actually your small particles actually grow in. So that's indeed what is said here, and that kind of stabilizer, that's for instance called an emulsifier or stabilizer or surfactant, or there are some kind of different names for that one. So anyway, you always need something that is actually then happening, that is becoming present at that interface to prevent that actually your small particles stick together and fuse. I've used a picture here from those who were present here yesterday. They see it already from that. That's for instance the reason that a typical emulsion is a mayonnaise, where you have an oil phase and a water-based phase, which is for your vinegar. You see already that making mayonnaise is not, if you just pour the two together, you will not have a mayonnaise. You need to have energy input on that one. But actually, there is also an important component. With just vinegar and oil, it will not work. Actually, an egg is a quite important component, because the egg yolk contains a lot of proteins, polar lipids, for instance, which are actually the components that are accumulating at the interface, and they are actually then making that you can stabilize your oil droplets in your water phase, in this case. So you always need kind of a third component, not only particles in the liquid, but there is a third component present at the interface, which is called an emulsifier or a stabilizer. So to protect your small particles from aggregation, flocculation, and coalescence. Previous slides were referring to what happens if you want to make small liquid droplets, nano-emulsions. Talking about small solid particles, nano suspensions, you will see that some of the techniques return. Typically also high pressure homogenization and microfluidization can be used to again, from bigger solid particles, create smaller solid particles. And actually these different techniques have been frequently included in different patents and have some kind of patented names. For instance, so you see actually here a kind of an overview, for instance. So we talk, for instance, here about diesel cubes. They are produced by high pressure homogenization. Or for instance, small particles produced by microfluidization, as the kind of nanojet technology, which was actually also patented. And actually in this case, there's also a third technique. So what can also be done with solid particles is that there can be a kind of a milling operation can be taking place. Media milling means that you combine your suspension with some kind of other very hard particles. And actually that whole suspension is then gradually, slowly stirred, so that actually the particles here, so your beads are moving over each other, and as your beads are moving over each other, so the particles that are present in between can be gradually grinded, can be gradually reduced. In that case, we're talking about nanocrystal technology. So for instance, the project that we had on nano suspensions a couple of years ago, in that case we were using that kind of media milling technique, so that nanocrystal technique, which was actually introduced here by Eden Nanosystems. I think it's an American company. So that's actually what we have in this case. Okay, for liquid droplets or solid particles, basically you start from bigger entities which you gradually reduce in size. But I said already in the beginning that actually there is also another way, and that's then typically happening with that kind of surfactant aggregates, is that actually individual molecules gradually combine, fuse, and make bigger entities in that kind of nanoparticle range. So if they gradually grow by themselves, then we talk about self-assembly. So they assemble by themselves. You do not need to have a lot of energy input. Self-assembly is the typical process for surfactants. Controlled precipitation is another way. If you start from a solution and actually you introduce precipitation of particles, also then it means that gradually you go from smaller to bigger scale. And so actually here to give you some examples, here so said already surfactant self-assembly in water. Water is actually there the driving force. Water tries to have, well, what you have in the surfactant is typically that there is a hydrophilic part here which likes to have contact with water. but that there is typically also a kind of a long alkyl chain, and actually water does not like to have contact with that long alkyl chain. So it's water that is the driving force. Water forces all of these kind of hydrophobic parts to be pointed away from the water, and actually you'll see later on that then depending on the properties of your surfactant, actually you can form this kind of spherical structures. They are typically a couple of nanometer in size. So then we talk about this kind of micelles, and actually what you see already from this kind of example is that such a kind of a micellar solution is actually quite transparent, because the particles are so small, only some nanometers, that's comparable to the size of individual proteins, and actually also a protein solution is actually a transparent solution. So that's what you have in this kind of micellar solution here, so obtained by having surfactants being present in spherical aggregates. On the other hand, for instance, well, if you add some more oil, we will see later on, you can also have some kind of swollen micelles. So if you have some more oil included in your micelle, then the oil can form the central part with the surfactant layer around it. That kind of swollen micelles are also referred to as microemulsions, as you see later on. And if you have some other kind of surfactants, some surfactants typically form that kind of bilayer structure, and maybe this kind of structure doesn't seem too unfamiliar. If you have some course on biochemistry, or that's the kind of typical structure that you also have for cell membranes. So it means that, for instance, the phospholipids are the building components of cell membranes, and it's indeed as such. So if you break phospholipids in water, then automatically they will assemble into this kind of bilayer structures, and actually this kind of bilayers, finally they will form a closed structure again. So then we talk about a vesicle or a liposome here. So what you have in that case is that you have an internal water part here, which is separated by a bilayer from an external water case. So what you can do in this case is actually, in this case, both entrap a hydrophilic component at the inside. Actually, vitamin C is actually very water soluble, so it will be entrapped in the internal part of your liposomes. But actually, you can also entrap here hydrophobic components into the bilayer, because here you have a more hydrophobic environment in the interior. Actually, in your micelles, you also use them to have some hydrophobic materials included, because actually also here, the core of your micelle is a hydrophobic part. So that's actually the one that's the reason that you use your surfactant in doing your dishwashing, or that you add soap to wash your clothes, is to make this kind of micelles, because then these micelles help to take up fatty material in the inside of your micelles, whereas normally the fatty material would not be entering into the water phase. So association here, spontaneous association, there's some important aspects about that cell association. Is that on the one hand, the concentration of your surfactant is important. So your concentration should be above the kind of a critical aggregation concentration here. As long as you're below that one, then you just have a simple solution here. So you should be above that one. Critical aggregation concentration, or in the case of mites, it's also known as the critical micelle concentrations, but critical aggregation concentration is actually more general. And if we then talk about micelles on the one hand, or liposomes on the other hand, well, I already briefly introduced that basically it depends somewhat on the, or it mainly depends on the properties of your surfactant here. So it mainly depends on how your surfactant looks like, and that's actually indicated in this so-called surfactant number, or it's also called the critical packing parameter. Actually, what you have in that number is that it expresses the cross-sectional area of the hydrophobic tail. So I said already, a surfactant typically has a long alkyl chain, which does not like to be in contact with water. So important thing here is about what is the cross-section of that tail. And on the other hand, you also have to consider the cross-sectional area of your hydrophilic head group, because there is typically a part in the surfactant that likes to have contact with water, and that's the reason for that kind of aggregation. So that's surfactant parameters, so making the kind of ratio. And let me explain this maybe somewhat more in this case. So what we can then typically have, the typical shapes we have was indeed, we said that you could form either this kind of spherical structures micelles, we could form that kind of bilayers in vesicles. Well, actually, it depends on that parameter. So if you have a molecular structure where the hydrophilic head group here is much bigger in cross-sectional area than the hydrophobic cross-sectional area, so that means that overall your molecule has a kind of a wedge shape here, with the hydrophilic part being the bigger one. And if now you start to have an assembly of these molecules, actually they're always assembling with the hydrophobic parts making contact with each other. And of course, if you stack all of these molecules together, then automatically they will stack in a highly curved structure, which is that kind of micelle here. And so you will typically have this for simple surfactants that only have one alkyl chain for every hydrophilic head group. So it means in this case we have a surfactant number below 1, because the cross-sectional area here of the hydrophobic part is smaller than the cross-sectional area over there. Whereas, for instance, phospholipids in water, and actually in general, most surfactants that have two long alkyl chains, they rather have a kind of a cylindrical shape here. So here your packing parameter, the surfactant number is about 1. The cross-sectional area of the head group is similar to the cross-sectional area of the hydrophobic pill. And of course, if you have this kind of cylindrical molecules and you start to pack them so that the hydrophobic pills are actually aligning with each other, then actually you will see that you will end up with more flat surfaces here. So then you have that kind of two parts where actually then two cylinders will point towards each other. So then you have that kind of bilayer architecture. And finally, the bilayers are closing them, then you form this kind of spherical liposomes or vesicles. So it's your surfactant chemistry that basically then determines your association behavior, so that determines whether micelles will be formed or whether vesicles will be formed. Right? And so talking about this kind of micelles, I said already, that's for instance the reason. So they form, you have this kind of spherical aggregates, typically only some nanometers in size here. It's indeed typically the reason why you use a detergent to doing your dishwashing, because actually spontaneously this kind of micelles will be formed. And actually here, what I said already is especially that the important thing about these micelles is that the central part here of your micelles is actually an ideal environment for hydrophobic compounds. So fatty materials can be taken up at the inside of the micelles, and that's indeed that's referred to as solubilization. The fact that kind of fatty materials normally they are not soluble in water, but if you have these micelles present in water, then you can take up that fatty material in your water with these micelles. So that's referred to as solubilization. And that was indeed the reason that you add detergent when you're doing your dishwashing, because then by adding the detergent you can nicely remove the fat and the grease from your plates and from your dishes, which is not the case if you just use water without micelles. So that's an important structure here. If you just have your surfactants in water, then actually you can form this kind of micelles. Now what is shown here is what happens. So if you have water and surfactants with mostly water, then you are in this region here where you form this kind of micelles. And what is shown in this diagram is that what happens if, for instance, you gradually add oil here. So as you go in this direction, it means here there is no oil, and then the oil content is more and more increased. What we know then is that actually if you add oil can be taken up by your micelles here. And so what will happen then is that as you add oil, that you go from pure micelles to actually micelles that include quite some oil here. So then we talk about that kind of swollen micelles here. So which then, well, here we have micelles of a couple of nanometers. This kind of swollen micelles can typically be some tens of nanometers here. And this kind of swollen micelles, they are also micro-emulsions. And the micro-emulsion that was coming from the traditional ages where we had the normal emulsions, which were big in droplet size. And as these ones were much smaller, then they were talking about micro-emulsions, which basically still form spontaneously, because it's actually micelles that you form and the micelles that solubilize your oil here. So they're still spontaneously, they're thermodynamically stable, and actually, because they're still so small, only some tens of nanometers. They are still quite transparent, or a little bit opaque, so we talk again about translucence here. And it's only if you add more and more oil, if there is actually, if you go in the region where there is much more oil than surfactant, then actually you will go in the traditional emulsion region here, and a traditional emulsion has typically a turbid emulsion, so that's the appearance like you have in milk, but that's not typically happening actually if there is much more oil than surfactant, whereas typically in a microemulsion, actually there is more surfactant than oil. So you see actually there already, also the mixing ratio is quite important here. If you use a lot of surfactants, so then actually you have enough of micelles to have all of the oil taken up just by solubilization. If there is not enough of surfactant, then the oil will really start to form individual droplets, which then have to be stabilized by a small amount of surfactant. So to summarize this one, we're talking about microemulsions, the traditional emulsions, which you can indicate as microemulsions, and nanoemulsions. So that maybe here the nomenclature is a little bit misleading, because normally you would think that, if you talk about microelectronics, then you're talking about something that is very small. So but in this case, it's actually essentially in size dimensions. So the microemulsions, that's okay, quite sure that they are the biggest ones. Actually, nanoemulsions are actually intermediate, and microemulsions are the smallest one. Whereas normally micro, like refer to micrometer, and the nanometer should be smaller. But that's due to historical reasons. First, we just think we're talking about emulsions. Then actually microemulsion terminology was introduced to say from we have something that is smaller. And nanoemulsion was actually introduced as a concept still later on, actually when that nanotechnology was incorporated as a term. And so then actually there is if you have emulsions which are actually some tens of nanometers, then we talk about nanoemulsions. They are basically a kind of a size reduced microemulsion here. So the nanoemulsions are typically bigger than microemulsions. These microemulsions are only some nanometers, they are typically transparent with a lot of surfactant. Your nanoemulsion is a kind of a size reduced version of the microemulsion. So that's actually what we'll have here. So, and actually what we'll see in this case is here again, what is important, I said already, one important thing about having nano size was that the gravity effect was prevented. Actually, here you see another effect, is that if you talk about nanoemulsions, then also depending here a little bit on the size, actually also the turbidity will be affected. So quite frequently, if you make your drops sufficiently small, then actually you can make that they are hardly opaque, so that you still see that they are not completely transparent, but that they are somewhat translucent. Which can be also quite nice, especially like in coating applications, can be important that you have a kind of not an opaque appearance. So that's actually also an important reason here. The visual aspect can be an important reason to reduce the size. Okay, maybe let's skip this one about, well, maybe just add this one as an example, because that's coming from Food Applications. It's about another kind of bottom-up approach, is to have that controlled precipitation. And for instance, here you see an example for the preparation of shellac particles in water. Shellac is a polymer here, which is not soluble in water, but it's actually soluble in ethanol. So if you start from a solution of your polymer in ethanol, and if you then gradually mix that ethanol solution with water, then actually, well, as your shellac is experiencing then a higher and higher water content, as it is not soluble in water, then your shellac will start to precipitate, and as such you can actually form shellac particles in water. So that's a way to make nanoparticles. And for instance, in this specific applications, quercetin was encapsulated, so the quercetin was added together with your shellac solution. And actually then if your shellac starts to form your particles, actually the quercetin can be trapped within the particles. So that's actually another way to make nanoparticles. This one I will skip. Because time is going by. So let's have a look then what you can do with this kind of nanoparticles, nano dispersions, what are typical applications specifically in food applications here. And what you see in this kind of overview is, well, there's two quite different applications. Quite a lot of applications are linked with improving the properties of food packaging here. And that's, I guess, still also the most widely used application. Is of course also the less critical application, because the packaging material, you do not eat it directly. It means the legislation is actually somewhat more strict. The other applications here is actually that your nanoparticles are really part of the food, and of course then you're consuming it, so that there is much more concern about, can this have some kind of negative effect, can there be some health effects. So here actually legislation is more strict, which is one of the reasons why it's actually so more complicated. So let's start with this packaging applications, and actually start with the fact that you can have improved packaging using nanoparticles here. Packaging is of course important to preserve food for a longer time. We know that any kind of biological material or foods that actually due to contact with, for instance, microorganisms, contact with water, contact with oxygen, contact with light, that actually a lot of things can happen. You can have chemical degradation, microbiological degradation, and that's indeed the reason to have a kind of a packaging applied to protect your food from external microorganisms, or to protect it from the effect of oxygen or light. So that's actually what we want to reach with this packaging, to have to create a kind of a barrier around the food. And talking about that barrier properties, well, that's then actually one of the big applications of nanoparticles, is that by introducing nanoparticles into the packaging material, that actually the barrier properties can be improved. That's, for instance, here illustrated with the barrier properties, for instance, towards oxygen, so to make that your oxygen cannot pass and cannot have access to the food. Actually, if you have a kind of a plastic material, a packaging material, then there can be still some kind of slow transition of oxygen, and of course that has to happen by diffusion, so your oxygen has to go from the one side to the other side. The main principles of having nanoparticles present is that by having your particles present in your polymer material, is that actually diffusion cannot follow the shortest distance, but that actually your diffusing oxygen must move around your small nanoparticles here that are present, and actually as such to create a much longer path, which actually largely slows down diffusion. You see already here that, for instance, typically here quite frequently non-spherical particles are used, nanoclays are typically used, and clays in this typical lake-like geometry is what you have, what you see here. It's actually somewhat illustrated further here. So what you have in this one is you still have your original polymer that is forming your packaging material, but nanoparticles are added, and so they can be spherical, but it's actually even better to have them rather in a kind of a non-spherical way, as platelets or tubes or fibers or wires here. And you see again actually that on the principle, without any kind of particles, your diffusion can go straight through. By having this kind of particles present here in your matrix, actually the diffusion has to follow a much lower path, and as such actually creates a much bigger barrier towards permeation. So that's one thing, actually to have improved barrier properties towards oxygen, moisture, for instance also, actually also improve barrier properties towards light, because your light will be more efficiently retained if there are particles present here. Typically also your plastic can sustain higher temperatures if you have especially inorganic particles present. But actually there is more than that. It's not only a barrier property, some kind of additional functions, like having additional a kind of an antimicrobial effect. And then basically we're talking about a kind of an active packaging, saying that you have an active function. So the barrier function is a kind of a quite passive effect. But an active function is that there is something additional, an antimicrobial, an antioxidant effect that is present. And that's surely typically the field of having nanoparticles present, because it's indeed well known that some nanoparticles have an antimicrobial effect. Silver nanoparticles are very well known to have a kind of a destructive effect on microorganisms. But also some kind of essential oils or essential oil components have a proven antimicrobial effect. I've indicated here thyme and oregano essential oils as typical examples. Or for instance, the main component in thyme essential oil is timol, which is shown here. Also, this kind of components have an antimicrobial effect. So if you can introduce this one into your packaging film, then actually they have a further protective effect on the food. Talking about this kind of nanoparticles, there are different mechanisms by which actually these nanoparticles can have a destructive effect, binding cell walls, actually introduce some damage. Generally also by reacting, by generating some reactive oxygen species, actually you can have a destructive effect. So there is some different ways that particles, especially small particles, can kill bacteria, can kill microorganisms, which is a desired effect. And you see indeed here that surely in this field there is a lot of commercial applications, so that's an overview that I found in literature. So actually you see already here that these are existing things, so there are existing products, existing brands here. For instance, if we're talking about this kind of nano-silver particles, you see them here in the product that is called Biomaster, and indeed that nano-silver was actually used as an antimicrobial packaging for fruits and vegetables. But you see that, for instance, also oxygen scavenging is an important one. Then actually using some other kind of material in your film, like for instance sodium oxide or some other kind of materials. In this case, even for fruits and vegetables, for instance, ethylene scavengers can be used here, as you will see in a product that is called soap. So actually here you see that there is surely here commercial applications of introducing small particles in your packaging material to introduce a lot of other functions than just the passive value functions, but that there is additional benefits of having the particles, for instance. Now coming back to that essential oils, so for instance the thyme essential oil, or thymol as a kind of a purified component. I said already that also these kind of components have proven antimicrobial effects, and actually also their effects can be quite, well, the antimicrobial effect has a number of reasons, where actually one of the most important things is that typically these kind of essential oil components, they are again hydrophobic, they are not very water soluble. Being hydrophobic, they will typically, for instance, interact with your cell membranes, will be taken up in the cell membrane. And if there is a lot of this kind of essential oil taken up in your cell membrane, actually it can disrupt your cell membrane to such an extent that actually the cell membrane becomes completely destroyed, or at least destroyed too much, so that actually the cell loses its integrity, and actually so the cell is actually killed. That's actually the most important mechanism that is reported, is actually by having your effect on your cell membrane. Now of course, if you have that kind of essential oils, remember it's basically a kind of an oil component, so it's not, it's hardly water soluble. On the other hand, typically it's much more easy to have things used in a kind of an aqueous environment here. So that's then indeed the reason for using emulsification technology. And if you use your emulsions sufficiently small, then we talk about nano-emulsions. And actually these nano-emulsions can then be used as kind of an edible coating, because actually you can make that you have your antimicrobial components present in something that you can eat here, rather than a kind of a plastic film. So what you do in this case is that basically, so you start actually here with your nano-emulsion here. So the nano-emulsion means that, for instance, you have your essential oil coming from thyme, which is actually included so into an aqueous solution. So you have water with these small emulsion droplets of your active ingredient, your thyme oil here. We said already that you will need a kind of an emulsifier to stabilize that system. And actually this kind of nano-emulsion can then be used as a coating on food products. That's, for instance, shown here more to the right. So what the easiest way is that, for instance, you just do a kind of a so-called tip coating. So if you have, for instance, here shown an apple, if you immerse it into your emulsion, and you take it out, then there will be a small film of your emulsion still sticking on it. Actually the water will evaporate, and actually what you will have finally will be a kind of a film here with your essential oil around it in the emulsified form. And actually your emulsified, the essential oil, the essential oils, they are food grade, so it's no problem to eat them. So here we have an edible coating applied, which actually will make that your material is protected for a much longer time against microbial contamination. But you do not, it's completely food grade, so that's an application that is surely here in progress. And so in this case, you need to have that kind of non-emulsion technology to have a kind of an aqueous dispersion here that needs to be treated. Actually, here you see kind of a schematic diagram of that edible coating. And also here, so then you see really that here you see an overview of non-emulsion applications here in coatings. You see that indeed it's especially here antimicrobial and also antioxidant purposes that are included with different components. I talked about thyme oil, see for instance here lemongrass essential oil can be used, cinnamon essential oil is also a quite known example, mandarin essential oil. So it's frequently essential oils that are used, that are emulsified. Here there is always a surfactant needed. You see for instance between 20 here mentioned, between 60, between 80 here. So there is a surfactant that is always has to be needed also to make your emulsion. And here you see actually indeed the reported advantages, the application actually on different types of fruits or vegetables. So this kind of applications have been described. So there's quite some well-known examples of that kind of edible coating technology. That's actually from another overview, basically is the same kind of information that you see that a lot of different essential oil components have been used, especially to have a better preservation here. You see emulsification techniques, and you see that typically when we talk about indeed about non-emulsions, because you have emulsion droplets which are very small, some hundreds of nanometers, but actually going down to only some tens of nanometers. And especially if you have a smaller size, then actually opacity is reduced, so you have a more transparent film. Let's then come to the other one. So packaging is surely an important one. That's the one that is most widely applied up to now. But actually there are also applications where nanoparticles, nanostructures are directly incorporated into your food to have actually improved properties in the food itself. And then basically we are at somewhat at the boundary of pharmacy. So then we talk typically about nutraceuticals, for instance, or about encapsulation, nano-encapsulation. So we'll include some examples here in the last cases here. So if we're talking about nutraceuticals, well, that need already in the name, so that's actually saying that there we are combining nutritional effects with what you want to do is, the effect is mainly that you want to prevent things. Normally pharmaceuticals are to make that if you're ill, that you get better again. What you want to do with the nutraceutical is that you try to prevent becoming ill, that you prevent some illnesses like cardiovascular problems, for instance, or other. Also indicated as functional foods or as fortified foods, so that there is some supplements, some additional nutrients added, which have a health promoting effect. And quite frequently, this kind of health promoting components again are as such poorly water soluble, so that quite frequently you have to include them into some kind of bottles to enable them to be included in the water-based system. So here indeed you see indeed some non-emulsions here with some proven health benefits. Here shows nutraceutical applications. Here actually you see things like curcumin being included, astaxanthin, vitamins can be included, resveratrol. So again, actually in this case, it's again some applications here of nano-emulsions here. So they are produced here by either spontaneous emulsification, by pressure homogenization, so that you include this kind of components into oil droplets of very small size, and as such they can be added to a food system to have this kind of improved functions. So,